Thank you very much. I would like to start by thanking the organizers for giving me the opportunity to speak and participate in this event. So I will continue in this morning's theme of extremal horizons. I will talk about joint work with David Katona and James, as well as work in progress with my supervisor, Maciek. So some of the things I will say at the beginning might sound familiar from James' talk earlier today, but I think it will be useful to have a brief review, so please bear with me. So the main motivation for this work comes from the problem of classifying stationary solutions to the Einstein equations. And in 4 dimensions, this is at least partially taken care of by the black hole uniqueness or no-hair theorem. It states that under certain regularity assumptions, every asymptotically flat and stationary black hole solution is uniquely specified by its mass and its angular momentum. This was originally proven in the 70s and has since been extended to Einstein-Maxwell and also to include certain extremal cases. However, in higher dimensions, the situation is much more complicated and this uniqueness is violated, as was shown by Emperan and Rial, who found a black ring solution in 5 dimensions, which is different from the natural generalization of Kerr, the Myers-Perry black hole. For example, they have different horizon topologies. However, they can have the same values of the mass and the angular momentum. And so the classification problem in higher dimensions is still largely open. But now if you restrict to extremal black holes, then there's an additional tool, the near horizon geometry, which you can use to attack this problem. And in fact, this is precisely how this uniqueness theorem was extended to certain extremal cases. So the idea is that the near horizon geometry is completely determined by data on a section of the horizon. So this is a codimension 2 problem, which is much easier to solve than the full Einstein equations. And once you classify these near horizon geometries, this will impose constraints on the exterior spacetime, as we've seen in James' talk, where this was used to prove uniqueness of the extremal Schwarzschild-de Sitter spacetime. And this is also the approach that I will take. So let me start by being a bit more precise about the setup. Following is based on a review by James and Harry Kanduri. So I'll start with a n plus 2-dimensional spacetime. So n is a Lorentzian manifold. And we're going to assume that it contains an extremal killing horizon H. So H is a null hypersurface, and there's a killing vector K, which is normal to H. And the extremality assumption means that the norm squared of the killing vector has a double 0 on the horizon. So d of k squared is 0 on H. Equivalently, the horizon has 0 surface gravity. And we will also assume that there is a codimension 1 compact submanifold M of H, which is transversal to the generator, so the integral curves of k. And so in this situation, we can introduce some nice coordinates, Gaussian null coordinates, such that the horizon is at r equals 0, and the killing vector is d by dv. And then we have some coordinates xa, which are an arbitrary chart on this compact manifold M. And in these coordinates, the metric looks like this. And it's important to note that there's this r squared here, which comes from the assumption that the VV component of the metric, the norm of the killing vector, has a double 0. And this assumption is actually what allows us to take the near horizon limit. So we consider the 1-parameter family of metrics obtained by multiplying r by epsilon and dividing v by epsilon, and then take a limit as epsilon goes to 0. And we arrive at what's called near horizon geometry. So this is essentially the same metric, but these x, f, and g are now evaluated at r equals 0. And so the point is that this new metric is going to be completely determined by data on M. It's going to be determined by G, which is just the induced Riemannian metric on M, by X, which is a 1-form or equivalently a vector field on M. So this 1-form is going to be important later. So I'm just going to mention that we could have defined it differently as well to show that this doesn't depend on any of these coordinate choices. So this 1-form on M is such that for all tangent vectors to H, if you contract V with the derivative of K, you will get a constant on N. So this X is somehow a natural thing that you can introduce in this context. And moreover, the extremality assumption means that when we take V to be K here, we'll get 0 because KA nabla AKB is 0 on the horizon, because I can commute these indices because by the Killing equations, and I'll get d of k squared. So this implies that KA XA is 0, which means that X has no dV component, which means that we can actually view X as a 1 from on M. And there's also this function F. So this a metric G, a 1 from X, and a function F, all defined on the manifold M. And now in contrast to James' talk, I will consider the situation where there is some matter. So we'll have some energy momentum tensor, which we assume to also have this near horizon limit. So again, it will be determined by a bunch of quantities on this manifold M. And what we now do is we will impose the Einstein equations on the original spacetime. So here the Greek indices refer to the big spacetime N. So now this one parameter family of metrics, depending on epsilon, will all satisfy the Einstein equations. When we take the limit as epsilon goes to 0, the near horizon geometry also has to satisfy the Einstein equations. However, the Einstein equations for this near horizon geometry is simply a set of equations on this cross-section M. And these equations are the following. So this function F that we had will be determined algebraically in terms of other data. So we can forget about F. And we end up with the following equations, where here and in the rest of my talk, all quantities are quantities on M. So G is the metric on M, R is the corresponding Ricci tensor, nabla is the Levi-Civita connection of G, and then we have this one form X, lambda is the cosmological constant, and then we have this matter terms, which I packaged into this PAB. And of course, there will also be some matter equations induced on M. And so this system of equations, together with the matter equations, is what I will refer to as the near horizon equations on M. And what we will do is we will now forget about the original spacetime and simply keep M and try to solve this system of equations on a compact Riemannian manifold M. So the outline of my talk, I will start with a brief review of the vacuum near horizon equation, which is what James talked about. And I'll review this Dunashvili-Chetty method of finding a Killing vector. And then I'll consider two extensions of these arguments. One is to Einstein-Maxwell theory. So we include a Maxwell 2 form. And the second extension is to the quasi-Einstein equation, which also has appeared this morning. So this is an equation of some wider mathematical interest that is very similar to this vacuum extremal horizon equation. And then finally, I'll talk about the generalized extremal horizon equation, which was introduced by Kaminsky and Lewandowski. So at least in 2 dimensions, this is a generalization of all the equations I just mentioned. And I will discuss a topological rigidity result for solutions to this equation, namely that every solution on a compact surface must be defined on the sphere. So this is somewhat analogous to Hawking's topology theorem for black hole horizon cross sections. But I want to emphasize that everything that I will be doing will be purely intrinsic and only uses M and doesn't depend on any embedding in any spacetime. So the vacuum case, so in vacuum, we have the following equation, which we've seen earlier this morning. And just to set some notation that I will use not just for this equation, but also for similar equations later on. I'm going to call a solution trivial if the vector field is identically 0. So in this case, M is going to be Einstein. And I'm going to call the solution static if the one form dual to X is closed. This terminology comes from the fact that when this condition holds, then the near horizon geometry will be static. And well, the simplest non-trivial example of a solution to this equation we can write down is the extremal Kerr horizon, where here, so X is going to be cos theta, and theta and phi are the usual coordinates on the sphere. And well, it's important to note that there is a Killing vector, an axial Killing vector, and this vector field X can be written in terms of K in this special way. And well, for a long time, there was the question of whether there are other solutions in 2 dimensions to this equation or not. And well, recently there was a breakthrough which was solved by James and Maciek using the following theorem, which says that if we have a solution on a compact manifold and this vector field X is non-gradient, then there must be a killing vector, and the killing vector preserves X. So this last part of the statement was proven in the general case in the appendix of the second paper. And well, the axisymmetric case was already pretty well understood. And since we now know that every solution has a, it follows that the general non-trivial solution is indeed given by the extremal Kerr horizon, possibly with a cosmological constant. And I'll say some brief words about the proof. So the idea is to use an ansatz for K in terms of an, at this point, arbitrary smooth positive function gamma of the following form. And then you do some calculations and you find some identity which allows you to express the norm squared of the Lie derivative of the metric with respect to K as a divergence plus a bunch of terms proportional to the divergence of K. So if you now choose gamma such that the divergence of K is 0, which, as James explained, can always be done, then an integration over the manifold using Stokes' theorem will show that this quantity, the integral of this quantity is 0, and since it's non-negative, it implies that K has to be a killing vector. No, this K lives on the manifold M. So we only have M, we don't have any space-time anymore. This is not the same killing vector as the one that defines the horizon. Yes. Yes. So X is tangent to the cross-section, so there is, and so is K. Everything lives on this cross-section. So once you know that K is killing, then you know that K preserves the Ricci scalar, and you can express the Ricci scalar using the near horizon equation, and you'll find some elliptic linear PDE for the Lie derivative of gamma, and some global analysis of this PDE will tell you that K has to preserve gamma, which then is equivalent to K preserving X. And the reason this is important is because it implies that K extends to a killing vector of the near horizon geometry. So this covers the vacuum case. I would now like to move on to the Einstein-Maxwell case. So we now have some energy momentum. Yes. For Schwarzschild, X is 0 and K is also 0. Ah, it's good. I should have mentioned. So this X, yeah, so X being non-zero is if the horizon is rotating, your X will be non-zero. Otherwise, here they are. But I should have mentioned that, yes, sorry. Yeah, so this is why there's this assumption that X is non-gradient, which is exactly what guarantees that K will be not 0. So this is why we need to assume this. Yeah. Good. So we now include some energy momentum. We include a Maxwell 2 form F. And you can show that this F also must have a near horizon limit. And since it's closed, it's going to be completely determined by a 2 form B on M and a function psi on M. So this 2 form is just the induced Maxwell field on the cross-section. And now you can go back to the equations I had earlier and simply plug in this expression for T mu nu, and you'll find the following Einstein-Maxwell near horizon equations. So we're now solving not just for the metric and the vector field X, but also for a 2 form B and a function psi, and they have to satisfy all of this. So the first equation is the same equation we had before, where P now is going to contain some matter terms involving B and psi. And the second equation is the matter equation. So this comes from imposing D Hodge F equals 0. So this is now this coupled system of equation that to try to solve. And just like in vacuum, you can write down the simplest non-trivial solution, which is now not so simple anymore, and the details don't really matter here. But the point is that, of course, it's going to be more complicated than extremal Kerr because we have this a magnetic charge P and electric charge Q around. However, there still is a killing vector K, and this vector field X can be written in terms of K in the same way as before. So there is some hope that this Dunevsky-Luchetti argument generalizes to this case. So to do this, I'm going to set n equals to 2, which, remember, corresponds to 4 space-time dimensions. So I guess this is the physically most interesting case. Now, briefly review what was known already. So if you assume that the solution is static, so the one form dual to X is closed, then actually the solution has to be trivial. This was shown first in vacuum by Crucial and Todd, and then it was extended to include a cosmological constant. So by trivial here means that X is 0, psi is constant, B is a constant times the volume form, and the metric has constant curvature. And so one way to show this, which is the way that Kaminsky and Lewandowski did this, is that for static solutions, there's an easier local argument that there has to be a killing vector. And once you have a killing vector, the equations become ODEs, which you can solve, and then you can see explicitly which ones extend to a compact surface, and it turns out that there are no non-trivial ones. And similarly, if you simply assume axisymmetry, again, you will get some ODEs, and it was known already, again, first proven in vacuum and then extended to a cosmological constant. So it was known already that the only non-trivial thing you can have is the extremal Kerr-Newman horizon. So just like in vacuum, the gap was, does every solution need to have a killing vector? And this is the main result in this work with James and David Katana, which is just like in vacuum, if we have a solution on a compact manifold with a non-gradient vector field. So notice that the gradient, in the gradient case, X is closed. So this is already covered by this result. So it suffices to deal with the non-gradient case. And in this case, there will be a killing vector. And moreover, this killing vector will preserve all the data, will preserve X, psi, and B. So to prove this, I'll first take a closer look at the matter equations, which simplifies in 2 dimensions. So this is the main reason that I'm restricting to 2 dimensions, because this 2 form will simply be given by a function times the volume form. And so the equation can be written like this. And it will be important to notice that these functions beta and psi cannot vanish simultaneously. So that's the following result. If we define rho to be the square root of beta squared plus psi squared, then either rho is identically 0, which is the vacuum case, or rho is strictly positive. And in that case, in particular, rho is going to be smooth everywhere. So the proof, at least on the set where rho is positive, M tilde, you can show that log rho satisfies a Poisson equation of the following form. So this comes directly from this matter equation. And then by standard results, such an equation has a solution on a compact manifold, which is unique up to adding a constant. So I'm going to call this global solution F, and consider H, which is log rho minus F. So H will be harmonic on M tilde. And moreover, H has to attain a maximum in the interior of M tilde, because as you approach the boundary, log rho will tend to minus infinity. And then, well, by the maximum principle for harmonic functions, H will have to be constant. And then rho is going to be some constant times e to the f, which is positive. And I should mention that there is an alternative proof in the following paper where they also looked at equations of this form. And they showed that the complex valued function f, the complex valued function beta plus I psi cannot have zeros. Yes. Simply connected, not at, no, definitely not. I may be assuming orientability to define this Hodge, that's all. Good. So now I'm gonna mimic the arguments of James and Maciek. The first step is to make this ansatz for K, and then write the equation in terms of K. And I'm going to be denoting in red, which is barely visible, but it is red, the terms that differ from the vacuum calculation. So there'll be an extra term, rho squared times the metric. So the extra term is pure trace. And now, well, of course, you try to generalize, find a version of this identity expressing the norm squared of the Lie derivative. And it turns out it can be done, and it looks as follows. And so here on the left-hand side, you will have strictly non-negative terms, just like before. On the right-hand side, we have a divergence plus a bunch of terms proportional to the divergence K. If we again choose gamma such that the divergence of K is 0, and then integrate, we find that in fact this quantity has to be 0. So we find not only that K is killing, but also that gamma times rho is constant. This identity is in some sense even stronger than. So I'll say some words on how to derive this identity. You start with rewriting the norm squared of the killing vector in the following way. So this is the same as in the vacuum case. And then you can get an expression for this last term using the contracted Bianchi identity applied to the near horizon equation. Notice that the extra term compared to the vacuum calculation was pure trace, and this pure trace terms do not contribute to this contracted Bianchi identity. So until this point, the computation is exactly the same. However, there will be a point where there is a triple derivative acting on gamma, and you'll need to commute some derivatives using the Ricci identity. And this is where an extra term gets introduced. And so at the end of the day, you end up with the identity in vacuum plus one extra term containing the matter. But notice that until this point, we have not used the matter equation at all. So now the trick is to try to rewrite this last term into something useful using the matter equation. And this can be done. So we can express it as something proportional to the divergence of K plus a total divergence plus a term that is of definite sign. And luckily, it has the right sign for the identity to work. And this is how you get the identity. So then, as I explained already, we fix this gamma in the same way as before. We integrate over the manifold to find that K is killing and gamma times rho is constant. And we go back to the last equation here. If gamma times rho is constant and K is killing, then this right-hand side is just 0. So we also find, we get for free, basically, that K preserves gamma. So we have to do much less work than in the vacuum case. And since gamma was since rho was 1 over gamma, we also find that K preserves rho. And so writing everything in the original variables, we find that K preserves all the data. And given what I said before, this proves that the only non-trivial solution to this Einstein-Maxwell near horizon equation in 2 dimensions is given by the extremal Kerr-Newman horizon. So this is a direct generalization of the vacuum result. So I'll now move on to the second application of the Dunajsky-Lichetti method, for which I need to introduce, or I guess this was already introduced, the quasi-Einstein equation. So this is almost the same as the vacuum near horizon equation, except we now have an arbitrary constant in front of the x squared term. So in the vacuum case, the constant here was 1/2. So for m equals 2, this is the vacuum near horizon equation. But now we're going to allow m to be any non-zero real number. So m is not any type of mass, m is just a parameter. And it turns out that it's the only parameter you can introduce. If you try to put a constant anywhere else, then you'll find that you can rescale things such that you can get rid of them, and there's actually only one. So the reason for looking at this equation is because it appears in various contexts. It has some relations to some projective metrizability problems. It's related to the Einstein-Waal equation and also to the problem of finding warped product Einstein metrics. And I'll talk about all of this in detail in my second talk next week. But for today, I'll just like to consider this equation in the context of trying to find a killing vector. And so solutions to this equation have been studied under various assumptions. For example, assuming that the one from dual to X is closed, or that X is divergence free, or the 2-dimensional problem assuming axisymmetry. And in all of these cases, it was observed that there is a killing vector of the following form. So for m equals 2, this is the same ansatz that we were using before. And for general m, it turns out that you have to put a 2 over m in front of the x term. And again, the question is, does every sort of non-gradient solution on a compact manifold have such a killing vector? And so by now it might seem obvious what to do. We make this ansatz, fix gamma such that k is divergence free, and find some expression for the norm squared of the Lie derivative and integrate. However, so this was done in the following preprints, but it turns out that it doesn't quite work. There are a bunch of terms that vanish exactly when m equals 2, and you can package them into this nice compact form, Ricci tensor contracted with k and with the gamma. But it's in general not clear whether this is 0 or not. So for a while it was unclear how to proceed. And I would now like to show at least a partial solution to this problem. So when m is bigger than 2 or less than 2 minus the dimension of the manifold, then in fact there is a killing vector of the desired form, and it preserves x. And so the trick will be to fix this function gamma slightly differently. So the first step is, yes. So it's true for m equals 2. The way I'm going to do it, I'm going to be dividing by m minus 2 at some point. So I'll just don't state it. I'll state it for m bigger than 2 right now. Yeah. Right. So the first step, again, is use this ansatz for k, plug it into the equation. And so this is the same as before, except that there is now some m around as well. And now we essentially do the same computation as before, but before we integrate, we multiply by a certain power of this function gamma, and we group the terms slightly differently. And you can get the following result. So here, given some appropriate restriction on m, for example, m bigger than 2, this left-hand side will be non-negative. Recall that gamma is strictly positive. And on the right-hand side, we have a total divergence. And we have a bunch of terms proportional not to the divergence of k, but to the divergence of gamma to some power times k. So of course, the trick will be to now fix gamma such that not k is divergence free, but this power of gamma times k is divergence free. And then we're in business again, and we can integrate and find out everything that k has to be killing. And of course, this h and v are complicated expressions that don't matter at this point. So we solve the same PDE as in the vacuum case. This is the PDE that gave us this function gamma such that k is divergence free. But now we take gamma not to be equal to psi, but to be psi to some power, psi to the 2 over n, such that not k, but this function times k is divergence free. And then we integrate, and we find that the following integral is 0. And well, what we're integrating for m bigger than 2 is non-negative. So we immediately find that k has to be killing. But in fact, we can do a little bit better. So we can use this just this linear algebra estimate to estimate the norm of a 0-2 tensor in terms of its trace. And using this, you can show that when m is less than 2 minus the dimension, the integral is still, the integrand is still non-negative. And so again, the same conclusion follows, k is killing. And when m is equal to 2 minus n, this approach will only tell you that k is a conformal killing vector. But this is one of these special values of n for which the equation has some nice conformal properties. It's related to the Einstein-Wahl equation. And using these conformal properties, you can show that actually, even for this m, there is a killing vector. And I'll come back to this next week. But for m between 2 and 2 minus n, as far as I know, the problem is still open. This method does not seem to work. I would expect the result to still be true, but this is, of course, just conjecture. In any case, once we know that k is killing, we know that, well, and we also know that k times this function is killing. So again, we get for free that k preserves gamma, which means that k also preserves x. And so indeed, there has to be a killing vector. And this has some nice consequences. For example, just like in the equations, for the equations I discussed before, you can now solve the general solution in 2 dimensions. And moreover, you can show that for certain values of this m and lambda, there are no compact solutions at all. So if I go back to the equation, when m is less than 2 minus n and lambda is not positive, this Ricci tensor is sort of too negative definite for there to be a killing vector. you can use some version of the Bochner technique so that there cannot be a killing vector commuting with X. So this result implies that, in fact, there are no non-trivial solutions on a compact manifold for these m and lambda. Okay. And I come to the last topic of my talk, which is the generalized extremal horizon equation. So what we do now is we allow both variations of the vacuum near horizon equation that we've seen so far. So we allow this constant in front of the x squared to be arbitrary. So this was something like 1 over m for the quasi-Einstein case. We now allow it to be any non-zero constant c. And we allow adding an arbitrary pure trace term to the equation. So again, this includes the Einstein-Maxwell case where we add this rho squared times the metric as the extra term. And since in 2 dimensions, the Ricci tensor is also proportional to the metric, we find that in 2 dimensions, this equation contains all the equations I talked about so far for different values of c and different functions f. So this is quite a general equation. And the result I would like to present is the following theorem, which states that whenever x is not identically 0, then any solution on a compact surface up to a cover must be on the sphere. And so this was proven by Kaminsky and Lewandowski by showing that such a surface needs to admit a holomorphic vector field. And I would like to present a different proof, which is based on the Poincaré-Hopf theorem. And this has the additional advantage that it imposes some restrictions to solutions in higher dimensions as well. So I'll just briefly recall, the Poincaré-Hopf theorem states that if I have a vector field with isolated zeros on a closed manifold, then you can calculate the Euler characteristic of the manifold by summing up the indices of the zeros of x. And the index is defined as follows. So we take a small coordinate disk around an isolated zero and use this coordinate chart to trivialize the tangent bundle. So then we can view this x as a map from this coordinate disk to Rn. And we restrict this map to the boundary of the disk and divide by its norm to get a map between 2 spheres of the same dimension. And this has a topological notion of degree. And this is precisely what we mean by the index of x. And so, of course, the trick will be to apply this Poincaré-Hopf theorem to the x appearing in the equation. In fact, let me write down the equation again, because we will need it many times. So symmetrized derivative of x with some constants times x squared plus some function times the metric is 0. Okay. Okay. So the proof will consist of 3 steps. We will first show that x has at least 1 0. And we'll show that any 0 of x is isolated. And finally, that the index of x at any 0 is positive. So then by the Poincaré-Hopf theorem, the Euler characteristic will be a sum over the indices of the zeros. The sum is non-empty by 0.1, and every term in the sum will be positive by 0.3. So we'll find that the Euler characteristic is positive, and given our assumptions on m, this implies that m has to be the 2-sphere. So I'll start with the simplest step, which is step 1. What we do is we take the trace of this equation to express f in terms of x, and then we contract the equation twice with x to get some equation involving only x. And you can write this equation in the following form. So the divergence of x over the norm squared of x is some non-zero constant. And now if x were to be nowhere 0, then x over x squared would be a globally defined vector field. However, the divergence of any globally defined vector field on a compact manifold has to change sign. So this is not possible since c is not 0. So we find that this cannot be globally defined. So x must have at least 1 0 somewhere. And step 2 is to show that any 0 is isolated. This will involve some complex analysis. We pick some complex coordinates compatible with the metric. And then, well, the metric and the one from dual to x can be written as follows for some complex function p and some real function h. And what we will now do is we'll look at the sort of trace-free part of this equation, which in these coordinates is the z bar component. So we fix a function f such that d by dz bar of f is p bar. Locally, this can always be done. And then the z bar component of the equation will tell you that a certain function is holomorphic. Moreover, this function vanishes if and only if p bar vanishes, which vanishes if and only if x vanishes. And since zeros of holomorphic functions of one variable are isolated, we find that every zero of x must be isolated. And we also find that not all derivatives of p, so not all derivatives of components of x can vanish at the point p, again, because holomorphic functions are analytic. This will be important later. And just to note, if we were to already know that M is a two-sphere, then this function f actually exists globally. We could introduce it by del bar of f is the 0, 1 part of the one form dual to x. So here the 0, 1 refers to the decomposition of the complexified cotangent space with respect to the complex structure. And I'm using the fact that every 0, 1 form on the sphere is del bar of some complex function. And then, well, this computation actually has some global consequences. It implies that this function times the 1, 0 part of x is a holomorphic vector field. Moreover, when you lower the index of this vector field, you get del bar of some function. And the only surface admitting such vector fields is the sphere. So this is what the approach of Kaminsky and Lewandowski is based on. They essentially show that there must be such a globally defined vector field without a priori assuming that M is a two-sphere. But so in this approach, this only appears after we already know that we're on the sphere. And so it remains to prove step 3, which is the hardest step. This was what I'm going to say now is motivated by this some considerations in the paper by Kushel, Sipka, and Todd, where they did some similar computations for the vacuum near horizon equation. And so the idea is that we're going to calculate the index of a zero from the equation using the following lemma by Milner, which states that when we have an isolated zero, then the index of the zero will be given by the determinant of the matrix of first order derivatives of x, at least whenever this determinant is not zero. And when this determinant not zero, we also get the fact that the zero is isolated for free, because it means that x is a local diffeomorphism. So the goal will be to calculate this determinant from the equations. However, the equation only prescribes the symmetrized part of the derivatives of x. So what we need to do is prolong the equation, introduce some function omega containing the anti-symmetric part of the derivatives. So that's just dx is 2 times omega times the volume form. And then the prolonged equation looks like this. And from here, well, at a 0 of x, this x squared term will disappear. So we can simply calculate this determinant. And it's going to be positive unless at this point where x vanishes, also both f and omega vanish. So this degenerate case, I'm not sure if it can actually happen or not, but even if it does happen, I do have an argument for why the index is still positive. It might not be 1 anymore. And this relies on showing that the determinant at such a point, such a degenerate zero, will have a strict minimum. So a useful example to keep in mind is x is the real part of z to the n plus z on C. So this vector field has an isolated zero at the origin, and the zero is of index n, because as you go around the origin, it sort of winds n times around the origin. So this has a zero of index n, and moreover, this determinant is 0 at the origin and positive in a neighborhood of the origin. And so the claim is that this is enough to guarantee that the index will be positive, and it is positive in this case. So in fact, you can, by slightly wiggling x, you can show that in this situation, the index of the zero will be the number of pre-images of some point very close to the zero. which indeed is n in this case. But I'm going to skip the technical details for this and just show that in this degenerate case, the determinant has a strict minimum at the point P. So this relies on this observation I made before that not all partial derivatives of components of x can vanish at this point P by the properties of this holomorphic function. So in particular, there exists some minimal k such that not all k plus 1 order derivatives of x vanish at P. And now the game will be to expand all quantities to leading order. So to leading order, this x squared term will not contribute. And so the determinant will look like this and will be determined by kth order partial derivatives of f and omega. And you can also derive some constraints on these kth order derivatives, essentially by applying nabla c to this equation, computing some derivatives using the Ricci identity, and then evaluating everything to leading order at the point P. And you'll find that there is a relation between the kth order derivatives of f and omega. And also, if you take the kth order derivative of f and take the trace on any two indices, you'll get 0. And so this implies that constant c, which is defined by minimizing the sum of the two squares appearing in this expression for the determinant over the unit circle, this constant has to be positive, because if there were a unit vector such that both of these expressions are 0, then using these constraints, you can show that actually all kth order derivatives of f and omega are 0. But that would imply by the equation that all k plus first order derivatives of x are 0, which contradicts the definition of k. So this constant c has to be positive, and then well, you can estimate this determinant to show that it must have a minimum at the origin. And then we find that the index is positive, and then by the Poincare-Hopf theorem, we conclude that the Euler characteristic has to be positive. And so if you impose, so this covers the two-dimensional case. If you impose some additional conditions, for example, if you impose that this function f is nowhere 0, then this proof, at least in even dimensions, will still tell you that the Euler characteristic has to be positive. So if f is never 0, we can never be in this degenerate case. And this prolongation will now involve a function times symmetric plus some arbitrary 2 form. But the determinant of this, as long as f is not 0, will always be positive. So we'll find again that x only has zeros of index 1. And you can also show that there has to be at least 1 0 using a generalization of the same method. So this also imposes some constraints in higher dimensions. So to summarize, I presented 3 main results in this talk. First of all, concerning extremal horizons in 4-dimensional Einstein-Maxwell theory. So every non-trivial solution to this Einstein-Maxwell near horizon equation is given by the extremal Kerr-Newman horizon. And moreover, for the quasi-Einstein equation, every solution on a compact manifold with a non-gradient vector field has a killing vector, at least given some appropriate restriction on M. And for the generalized extremal horizon equation, every solution has to be on the 2-sphere, or RP2. So some open problems are still, of course, quasi-Einstein equation with M in this finite interval. Is there a killing vector or not? And also one could consider extending this proof by James and Maciek to higher dimensions and to other theories. But I'll finish here. Thank you very much.
Okay, thank you very much. Are there any questions?
Yes.
With this last equation, you analyzed have you thought about the proof that you must have a killing field in that case?
I've thought about it, but I don't, it feels too general to be true. But again, I don't have any example without a killing vector, so I don't know. Yeah. Yeah, everything was smooth. Assumed. Everything was assumed to be smooth.
So in 4 dimensions, modeling, there is also the other chargeable solutions like the symmetric amount of fixed or constant. I don't know if those have extreme limits. There is an extreme limit. And I'm wondering how are those excluded?
I'm not sure if they have an extremal Killing horizon,
Right, but
then there will be
the
such a
thing
thing.
that said like two black body there. No, like,
No, so the statement is that you can look at the horizon of one of them, take the extremal limit, and you'll find the extremal Kerr-Newman horizon. It doesn't mean that the space-time is extremal Kerr-Newman. It means that the horizon is the same as for extremal Kerr-Newman.
Take the speaker again.